In the mid to late 19th century and the first part of the 20th, many hydraulic engineers had been hard at work developing equations we still use today: Darcy, Weisbach, Shazy, Manning, Hazen, and Williams. In 1930, Hardy-Cross developed a method of solving for hydraulic properties in a pipe network that was much more efficient and easily used than then current methods, and enabled many problems to be solved even before the advent of computers. These innovations enabled better design of pipe networks for water distribution. By the 1950s and 1960s, it was becoming apparent that waters in the U.S. faced serious problems in terms of pollution and other issues of water management. When we do not take care of our water resources, many difficulties can arise. Here in Tucson, one of the biggest problems related to water was that people started to take more water out of the aquifers than was replaced naturally. The level of the water table dropped dramatically, and the Santa Cruz River, which had historically flowed year-round and provided water to Tucsonans, began to go dry for most of the year. On the national scale, the critical moment of realization about water problems came when Ohio's Cuyahoga River burned in 1969. The fire was one of several that had occurred there and elsewhere, but it served to draw attention to the terrible water quality problems caused by improper disposal of industrial chemicals. In the shadow of the Burning River incident, Earth Day was established in 1970, the same year that the Environmental Protection Agency, or EPA, came into existence. And the landmark Clean Water Act was passed in 1972 when Congress overrode President Nixon's veto. In 1974, the Safe Drinking Water Act established standards for concentrations of many substances in drinking water. Here in Arizona, the construction of the Central Arizona Project Canal began in 1973. The division of Colorado River water amongst 7 western states, with an allotment for Mexico, began in 1922, with final approval of the Colorado River Compact in 1944. After over 20 years of lobbying by Arizona residents and politicians, the construction of the CAP Canal was approved by President Lyndon B. Johnson in 1968. This system of canals and pumping stations brings water to Phoenix and Tucson all the way from the Arizona-California border. The project cost over $4 billion. Today, Arizona's share of the water from the Colorado is 2.8 million acre-feet per year, or enough to support about 2.8 million families of 4 annually. Elsewhere in the world, water innovations continued as well, with Kuwait in the 1960s pioneering the use of seawater desalination technology using a method known as multi-stage flash evaporation. In the 1970s, the Aswan High Dam was constructed in Egypt, forming the world's 3rd largest reservoir along the Nile River, a project that produces electricity and reduces Nile flooding, but required thousands of people to relocate and some ancient monuments to be razed to keep from being flooded. And in the 1980s, a South African engineer named James Barnard developed the Barden-Foe process of wastewater treatment, which can remove many more nutrients from wastewater with fewer chemicals. The 1980s saw 2 major pieces of water legislation passed in the U.S. The Safe Drinking Water Act amendments of 1986, which set maximum concentrations allowed in drinking water for 83 contaminants, and the Water Quality Act of 1987, which regulated stormwater runoff and non-point source pollution, like that which comes from agricultural areas. In 1993, nearly 1/4 of the population of Milwaukee, Wisconsin, was sickened with the parasite Cryptosporidium, which was contaminating the public water supply. 100 people died, and direct medical costs were over $30 million. The Milwaukee outbreak was one of 10 Cryptosporidium outbreaks during the 1990s. In 1996, the UV waterworks was invented by Ashok Gadgil. The portable unit can purify hand-pumped or hand-poured water at a cost of less than 1 cent for 60 gallons, making it a feasible solution for developing areas. Around the year 2000, Geographic Information Systems, or GIS, started to be used in public water systems to detect leaks, which can be a major source of lost water for utilities. The early 2000s also saw several environmental and public health disasters, including extensive mercury contamination in fish from the Great Lakes, the sickening of 2,500 people and deaths of 7 due to E. coli contamination in the public water supply of Walderton, Ontario in 2000, the release of 100 tons of chemicals into China's Songhua River, an attempted cover-up by officials in 2005, and the 2008 release by the Tennessee Valley Authority of over 1 billion gallons of coal fly ash sludge. and subsequent federal investigation into whether TVA intentionally misled residents about the safety of the spill materials. Also, the World Glacier Monitoring Service reported in 2008 that the accelerated melting of major glaciers will adversely affect power generation and drinking water supply in South Asia and South America. So what happens next? Humans have developed ways to move water across mountain ranges, transport waste, and treat wastewater back to a quality that meets drinking water standards. We have developed better ways to design water distribution systems and model the hydraulic and chemical properties of water. But there are still over 1 billion people without access to clean water and over 2.5 billion whose access to sanitation is inadequate, and contamination of water supplies by industrial chemicals and microorganisms can still threaten people's lives even in countries where safe drinking water is the norm. The United Nations says that with regard to the Millennium Development Goal to cut in half by 2015, the proportion of the population without sustainable access to safe drinking water and basic sanitation, the world is on its way to meet the drinking water target, but that the sanitation goal appears to be out of reach. The world is also running out of its traditional supply of phosphate, a key ingredient of fertilizers that greatly increase the productivity of agriculture operations worldwide. This Hubbard linearization of world phosphate rock production indicates that the rate of extraction is already beginning to decline, while population is still increasing. And at least 2/3 of the remaining phosphate rock supply is in Morocco, which may lend an interesting political dimension to the continued use of phosphate rock. One alternative supply of phosphate is to recover it from wastewater or even directly from urine in systems that can separate waste right at the toilet. Without a doubt, engineers will play a major role in continuing to ensure and expand access to clean water in the coming decades. From simple devices like the Tippy Tap that promote hand washing, which can reduce by almost 50% the risk of diarrheal disease, to basic water treatment methods like solar disinfection and slow sand or ceramic filtration. Engineered devices that can be made available to developing areas at low cost can greatly reduce the effects of waterborne illness. And from improving desalination methods, which transform saltier water to fresh, to developing real-time sensor methods to detect contamination in public water distribution systems, engineers are on the cutting edge of innovation for even the most advanced water systems. In this unit, we'll start out by reviewing what we know about water and delve more into why it is challenging to provide access to clean water. Then, we'll look at the 4 elements of water access: quantity, quality, reliability, and cost. We've already seen these elements at play throughout water's history, from Roman aqueducts bringing sufficient quantities of water into Rome, to John Snow breaking the Broad Street pump handle to protect Londoners from poor quality water, from building dams to ensure a reliable supply throughout the year, to the development of the low-cost UV waterworks treatment. As we progress in the unit, we'll look at each of these aspects today and how engineers are improving lives with respect to water access.